Hi everyone, my name is Ivan Blinkov, and today I'm going to tell you a story about how we extended YDB with Postgres compatibility. A couple words about myself. I work in database development industry for well over a decade. Over this time, I worked on a handful of DBMS products, including two open source ones. So previously, I worked for 7 years on ClickHouse. You heard about it on the previous talk. And my current role is Vice President, Product and Open Source at YDB. Today's talk will consist of three main parts. First, I'll explain what's YDB and why it needed Postgres compatibility in the first place. Then we'll explore possible approaches to making a database product Postgres compatible. And finally, we'll take a closer look at YDB's approach and lessons learned along the way of this project. First of all, why YDB needs Postgres compatibility? We have to start with explaining what YDB is. It's another open source database management system that was designed for large-scale use cases. So typically, unlike Postgres, it's run on large clusters. Like we're talking like millions and tens of millions of transactions per second, tens to hundreds petabytes of data sets, this kind of stuff. And also it was designed for mission critical workloads. So for applications that can't afford to lose even a single row of data or have some inconsistencies. So it provides serializable isolation level for transactions and supports surviving even major outages like the whole data centers going down. So with these kind of properties, typical YDB use cases, you can see industries on the right. And it's not hard to notice that most of them handle money one way or another. So that's when it becomes critical that data is always correct and always available. And there are also a bunch of logos of our users, but you likely won't recognize any of them because they're from other parts of the world. So historically, YDB started as transactional database, just like Postgres. But over time, it evolved more to like a data platform. So we also have column and tables similar to ClickHouse. And these first two features are usually referred to as HTAP, hybrid transactional analytical processing. There was a talk about of this category of databases yesterday. And also we have built-in topics similar to Apache Kafka topics that can be used either for ingestion, for buffering and ingestion, or for outbound data in change data capture and like long distance cluster replication and other stuff. But they're out of scope of today's talk. So, and also it's important to understand some context about history of what's going on. So YDB is decade-old technology, but only 2 years in open source. So it started in 2014 as a proprietary technology for a large group of companies called Yandex. So most of their businesses are B2C, so working with end users, with like physical people. And they have like hundreds of millions of users, and again, many of them are working with money. And that's why they decided to invest early on into reliable database technology, because like doing sharding Postgres or MySQL or whatever isn't feasible on such scale. In 2020, they launched yet another business, which is basically a public cloud provider similar to Amazon, Google, AWS, Google, or Azure, but for some local regions. And that's where YDB was first publicly visible to outside the world. And 2 years ago, YDB was published in open source on GitHub as an open source project under Apache 2.0 license, which is one of the most permissive open source licenses, allowing even commercial use for free. And one of the first things we learned after going open source is that unlike in-house users that are mostly building new stuff from scratch, people who are using open source databases mostly use other existing tools and can't really afford developing some complex database migration projects. So they really were asking for compatibility with existing ecosystems. and we compared a few of them that are around, and PostgreSQL had the most tools around, the most vibrant community, and that's why we chosen to invest into this project of making YDB compatible with Postgres, and that's what the rest of the talk will be about. Early on in this project, we settled on our goals, what we wanted to achieve with this. So, as I said, we wanted to allow people to keep using the tools they are used to, but also gain all the positive properties of YDB that I talked about in the beginning, all this consistency, scalability, fault tolerance, and stuff like this. And also we wanted what I call interoperability. We wanted them to be able to use YDB native features and Postgres features kind of in the same environment and get benefits of both worlds if they need to. So first, let's explore how it's possible to make an existing database technology Postgres compatible. To talk about this, we'll use these kind of diagrams that are super high level illustration of how any DBMS processes queries. So it's not specific to Postgres and not specific to YDB, like most DBMS work roughly the same way at this level of detail. Let's walk through this diagram to explain what it means. So first, there are two kinds of arrows here. One arrows are, you probably can see it, double-ended, which denote data moving through the system. They're double-ended because data moves one way during request processing, and then roughly the same way goes back when response is ready and needs to be returned to the client. So client usually prepares a query on their side, sends it over the network using some sort of wire protocol. So wire protocols for database are not standardized, so most DBMS have their own, and Postgres has its own protocols, and likely it has specification, what needs to be sent over the network, and what all these client libraries and tools send. And then there's a SQL parser that kind of processes text query and prepares some intermediate representation of what the user asked to fetch. And then optimizer takes this intermediate representation and figures out the most optimal physical way how to actually do it. Then launches execution of this physical phase, which might call for some functions like multiplication, concatenation, this kind of stuff. It operates on some data types, and also it fetches the persisted data from storage, if it was a select query. So the idea is that we use diagrams like this to explore various approaches to making a database Postgres compatible. Let's take a look at the first approach, which is called implement everything from scratch. Here we introduce also two colors of blocks. So black blocks are meaning that we'll take this component from original implementation, in our case from PostgreSQL, and blue blocks means that we'll take we won't take this component from anywhere and build our own. So in this case, you can see we are taking original Postgres clients, client libraries, etc., because we want to be compatible with them. But the rest of the system is implemented from scratch. That's what database developers typically do when they want to use some fancy programming languages like Rust or Go, which are not really that convenient for using older code bases like PostgreSQL's. So, and also all of these examples are not made up, so they have real implementations in the world and in open source as well. So, and for each approach, we'll explore like their trade-offs and advantages, disadvantages. So, for this approach, you have the most freedom to implement the system the way you want it, because you are basically writing the whole of it on your own. And you can optimize anything you want, you make it suit any requirements you have, make it distributed, whatever, so it's all in your hands. But the downside is that it's really hard to make it fully compatible, because database management systems have a lot of corner cases where they behave differently, like it's not always documented and stuff like this. And also it's the most human resource intensive way because you don't really leverage an existing code base in open source and writing everything from scratch. Next approach is kind of almost the opposite. So basically, it uses most of PostgreSQL code base, like most of the runtime and all front-end part. And the idea is that you have also some sort of distributed goals, or maybe you want to make it more secure or something. You might replace only the lowest layers that not so much visible from users. For example, storage layer. And in this case, the advantages and disadvantages are kind of flipped in a sense that you are getting the most of compatibility with original Postgres because you are using so much of its original code base, so your system will behave almost the same. And also it's relatively easy to move to next PostgreSQL version when it's released because you are changing only a relatively small part of it. And you can even support some extensions that don't really rely too much on how data is stored. But in the end of the day, projects like this end up maintaining a PostgreSQL fork, which is how you do it on how you do it. It depends how complex it is. So if you really touch only the storage part, it will be like really relatively easy to maintain thing. But if you kind of don't control what you actually change from the original code base, it might become really like full-fledged fork that not really compatible with the original system. And I think the main disadvantage of this approach is that you are really limited in innovation. So because you are using so much of Postgres code, you don't have much space to improve on it without contributing patches to the mainstream, which you could have been doing without any separate database project. Next approach kind of mitigates the issues with the previous one in a sense that it uses official PostgreSQL extension APIs to change things that also might be essential for your use case, for your database idea. And it takes the whole Postgres code, even the storage layer, typically, and it's the most clean way because it's like don't fork Postgres. You don't have. It's the easiest to maintain, but you become also limited in innovation by what PostgreSQL exposes allows extensions to do. So again, you cannot change things that Postgres wasn't designed to be where it wasn't designed to be extended. Let's take a look at YDB's approach to this. What we did, we kind of went through component to component, and given our initial goals I talked about in the beginning, we considered what's the best way to handle it. So let's walk this path of query execution again and see how reasoning kind of ended up to these colors we see on the slide. So clients, again, we want to take original ones because that's what we're compatible with. But wire protocol in original Postgres has some historically weird implementation where it forks an operating system process for each client connection, which is a really resource-intensive operation and kind of limits how many connections you can have, and that's why people invented these kind of proxies that reuse connections and stuff like this. And this forking also wasn't really compatible with how we historically did internal concurrent processing and execution in our binaries. So we had to rewrite the wire protocol using the Postgres specifications, which allowed us to multiplex multiple connections in the same operating system process, thus allowing to handle more connections per server than original Postgres can. But the downside was that we had to kind of patch the remaining components of Postgres we took to replace global variables with local ones. Then SQL parser. It's kind of one of the most tricky parts of most SQL DBMS. Even though SQL is a standard, like it's 1,600 page long document explaining how database should behave, but it still has a lot of room for interpretation. That's why most SQL DBMS are not compatible with each other, because even though the standard covers a lot of parts, it doesn't cover, for example, what queries should return. My favorite example of this is query select 1 divided by 0. Like, there are multiple ways what it could return in theory, like error, null, or infinity. And there are DBMS that return all these possible values, even for such simple query. So we had to take original parser from Postgres, because that's kind of the most prone for compatibility issues part, and then convert its intermediate representation to our own terms, so we can reuse all this optimizer and query execution layers of YDB, so we can leverage the same distributed transactions and properties we wanted to keep according to our goals. But then during execution, there are parts that also have some complex semantic, like what functions should return, what data types we operate on, and how they should behave. These parts also had to be taken from Postgres. So with this approach, we kind of kept the key properties of YDB, but also becoming pretty close in compatibility with PostgreSQL. Given all of these data types and functions and tables, they are all in the same environment and namespace. It allows people to like start with Postgres and slowly migrate to YDB native stuff, or live forever on Postgres compatible mode and maybe use YDB functional features only occasionally. The whole project was quite a lot of work to integrate all these pieces together and figure out the best kind of way to do it, and research around it, and upgrading to each upcoming Postgres release is kind of in between of previous approach we discussed. So it's more complex than compared to extension, but easier than maintaining a fork. So for example, recently we upgraded from 14 to 16, and it was 1 week of one engineer's work, and upgrading between minor releases usually 1 day of engineer's work. So it's tolerable. Lessons learned, we kind of confirmed that only Postgres is 100% compatible with Postgres, but deliberately making your trade-offs and setting your goals can get you pretty close without any major kind of downsides. And also, I didn't have time to cover it in more detail, but in such projects, testing is really crucial. So basically, we took all ways to test this compatibility humanly possible. So we took all possible existing tests, even like we tested examples from documentation work the same automatically, and that allows to get confidence that it's actually pretty close to compatibility. And as some final notes, I want to remind you that YDB is 100% open source. So the core platform is built from scratch in C++. We have SDKs and integrations in most major programming languages, documentation in Markdown. You can find us as YDB-platform at GitHub. And we're really looking for contributors. So if you're into stuff like this, it's pretty hardcore, but also fun. Come check it out. And if you're interested in YDB as a product, check out our website, ydb.tech. That's it. Thank you. Any questions? Yes.
Okay. Why they build YDB and then it wasn't like Blinkov?
Yeah, so historically YDB was a transactional database. So it was about handling the current state of applications. So typical use cases are like, for e-commerce business, it's like state of the cart and orders. For taxi business, it's like state of, again, like of where person needs to go and stuff like this. So it's about what's happening right now, and kind of making sure that we don't lose orders, like everything is consistent, like balances are okay and stuff like this. And ClickHouse originally started as system to keep clicks of people on the internet, which has much more relaxed requirements in terms of, like nobody really cares if you lose a few clicks somewhere, if there are like many of them. So it's kind of the beginning. And then like ultimately over the years, like database projects choose their own path. So YDB goes this kind of data platform way. So we have analytical tables. They are pretty close to what ClickHouse were doing at the time. But also they have properties of consistency. ClickHouse doesn't have, like, they're like give simplicity of working the same platform, but not necessarily designed to be used just for it, just for them. And the same goes for topics. They're also like it's easier to have topics inside the same like environment because you can have transactions between, like between tables and topics, which are much more complex to do. For example, if you have Postgres and Kafka separately because they're different systems. ClickHouse basically went all in for this analytical world. So, and they're doing cloud offerings and stuff like this.
So do you consider yourself competing with single store YDB?
Yeah, if you were here yesterday, there were like quite a few HTTP databases that are doing something along these lines. Actually, the leading ones are commercial ones. So like, like Oracles and SQL servers. But there are quite a few open source alternatives, and there are like a lot of trade-offs on how they're implemented. So this is a high-level talk, and to get to the details, what's the difference is, you need to go deeper in trade-off, because there are a lot of trade-offs in all possible implementation like approaches and details.
Do you have like a single storage engine for all and
Well, even here, like the engines are kind of different. So they operate on the same data types. They use same lower layer storage, for example. But you can't really build generic engine for everything because it will be slow in some cases. So that's why people usually, like at least we do, build a bunch of specialized engines that look similar to users, because they use like same syntax, same endpoints, same SDKs, same like, but under the hood there are actually a bunch of specialized things to make it efficient, because at such scale, like each % of performance counts.
I'm curious about, compared to Cockroach DB, what advantage does YDB have?
So they're comparable products in this transactional world, in a sense that they also distributed database designed for consistency. So Cockroach also has serializable transaction isolation like YDB, which is even more strict than Postgres itself. So even this cluster can be more reliable. So in transactional world, they're comparable. But as I said, like YDB is going to this kind of platform thing. So as far as I know, Cockroach don't really have analytics or topics. So you'd have to integrate with some other stuff. Also, Cockroach went this kind of, where is it? Like this way because they're in Go. It's kind of debatable how well they kind of mimic the original Postgres, but some people find it okay, some don't. So I think we can do better with. We started later going Postgres compatibility, so as I said, it's only like 1 year and something old project, while Cockroach was aiming for this from the beginning. So I think right now we're kind of lagging behind, but I think with reusing PostgreSQL original code, we can get to much better level of compatibility, like in short-term, mid-term run. So this is a kind of trade-offs, and also they're designed differently if you go to architecture. So they're also on paper look the same, but implemented really differently. For example, they do log structured merge trees on the row level, like on rows of tables. And we do log structured merge tree, like this, kind of maintaining up-to-date information on a lower level on blobs of data that are actually stored. And we store not local file system, so we operate on top of raw block devices. Actually, I'm talking about them like in 2 weeks in Hong Kong, but hardly someone will go there. So they're designed differently, interpret differently, but on a high level, Cockroach and YDB have this distributed transactional database feature that you can, if you care only about this part.
Okay, thank you.
Any question? Okay, thank you.